The ionosphere is an important part of the near-ground space environment. The ionospheric total electron content is an important parameter that has some serious impact on satellite navigation. Accurately predicting the TEC is, therefore, very important not only to ensure the stability of a radio system, but also for pre-earthquake identification, among other fields. To improve the accuracy of TEC predictions, a new combined intelligent prediction algorithm was proposed by combining the International Reference Ionosphere Model, TEC statistical learning model, an artificial neural network, and a genetic algorithm. The training dataset of the model consists of solar activity parameters, time, TEC data predicted by the machine learning model and IRI model, and actual TEC data. The core of the TEC prediction model is the backpropagation neural network. We use the above data as a training set to train the neural network. The weight and threshold of BP-NN were optimized using a multi-mutation and multi-cross adaptive genetic algorithm. Finally, the combined machine learning method was used to predict TEC data, and then its prediction accuracy was analyzed and compared with other prediction models. The first step was the measurement of model input data. We obtained the original TEC data for 24 hours from 2004 to 2022 in Athens, Greece. 5,184 sets of data were obtained. To ensure that the filtered data waveform was close to the original data waveform, as well as to suppress interference and supplement missing data points, we used the data to carry out mean filtering. The TEC is easily affected by solar activity parameters, in particular by F10.7 and sunspot number. In addition, we introduced 3 time parameters: year, month, and hour. We also used the predictions of the IRI and the machine learning model as inputs to the model. And we used the Fourier function to simulate the daily variation in the ionospheric TEC. Next, we discussed the core algorithm of the model, BP-NN optimized by multi-mutation and multi-cross adaptive genetic algorithm. The BP-NN is a neural network with 8 input neurons, 1 output neuron, and 2 hidden layers. The multi-mutation and multi-cross adaptive genetic algorithm optimizes the weight and threshold of the BP-NN, improves its computational efficiency and accuracy, and reduces the error. Next, we discuss the prediction of TEC data. By looking at actual TEC data, we defined 2015 as a high solar activity year and 2020 as a low solar activity year. We use the IRI model, machine learning model, BP-NN, GA-BP-NN, and MMAdapGA-BP-NN to predict the TEC in high and low solar activity years, and calculated the error between them and the actual TEC data. By calculating the root mean square error and other evaluation indicators of the forecast data in different models, we find that the prediction error of the model is larger in the year of high solar activity and the month of relatively intense solar activity. By analyzing the day and night forecast error separately, we find that the day forecast error is larger than that of the night. The structure of the model established in this paper is shown in the figure. MMAdapGA-BP-NN has a higher accuracy and a better prediction effect than the IRI model. Taking the Athens station in Greece as an example, the root mean square errors of MMAdapGA-BP-NN in 2015 and 2020 were 2.84 TECU and 0.85 TECU, respectively, which are 52.27% and 72.13% lower than the IRI model. Compared with the typical neural network model, MMAdapGA-BP-NN has a better prediction effect and is more stable.